In this video, we're going to look at a really important property, that the determinant of a product of matrices is the product of the determinants. Okay, this is very nice because, with matrices, we're very restricted with products. They're not commutative, so we can't do things like we like with numbers. But this is a really cool result, and it's really nice and we're very blessed that, this property is there. So let's talk about what would happen if B were singular. Because in the proof I'm going to show you, I'm going to assume B is invertible. But let's see what happens if B is singular. Well, if B is singular, then its determinant would be 0. And think about why, if B is singular, then A times B is also singular. Okay? So think about why that's true. Because if B is singular, then the right side would be 0 because this determinant is 0. And if that means that AB is also singular, then its determinant is 0, so 0 equals 0. So think about that. But I'm going to focus on the case where B is invertible. Okay? Now, there's a pretty clever proof. I first saw this proof in Gilbert Strang's book, and I think it's a phenomenally clever proof. So what we're going to do is we're going to define a function. We're going to call it det, and that stands for determinant. And we're going to define it to be the product, the determinant of AB divided by the determinant of B, okay, where B is any invertible matrix. Okay, we're going to prove that this is actually the same determinant function that we've been talking about all along. Okay, so whether we do the determinant the old-fashioned way or we do the determinant of AB over BA or over B, then we get the same answer. And that's really what we want to show. And we want to prove that this is a determinant function. To prove that the determinant of A defined this way is a determinant, we have to prove that the defining properties are valid for this function. This function satisfies those three defining properties. So just some notation here. I want to call the product AB as C, and I'm going to denote A and C the standard way. And let's prove that the determinant of the identity matrix is 1. Again, proving it using this definition. So this det of identity, according to that definition, is identity times B, the determinant of that product, divided by the determinant of B for any invertible B. Okay, well, IB is just B because the identity matrix times any matrix is the original matrix, and we get 1. Okay, that's it. So the property 1 satisfied by this det new fancy determinant function. That's good. Now the next thing we want to show is that the second defining property holds. Okay? And what I want to show you is, so let's say I have row 1, row 2, row 3. Okay, this is my A matrix. And I multiply that with B and I get C. I'm going to call this row 1 of C, row 2 of C, and row 3 of C. Okay, let's clean this up here. All right, let me highlight this one and this one. Now we know that with matrix multiplication, the product of two matrices is such that what this does is the first matrix contain the first row of the first matrix gives the first row of the product matrix. Okay, and so this yellow only depends on the yellow, and this pink only depends on the pink. And so if I were to interchange those, so if I were to put the old row 3 as row 1, keep row 2 the same, and put the old row 1 as row 3 times b, then that gives me exactly the same entries but in different positions, okay? So now that's here and that's here. So then what I would get in the answer here is I'd get the old row 3 of C in the first row position. Row 2 of C doesn't change. And what used to be the first row of C now is in the last position. So this is a basic property of matrix multiplication. And so, okay, so why is this necessary? Well, if we can think about these, then it's very easy to see that the determinant of the product will change sign when we change two rows of A. So basically, interchanging two rows of A changes the sign of the determinant because they would change the sign of this numerator. Okay, changing two rows of A will change two rows of AB, the same two rows, and that'll put an opposite sign there. And so the denominator is not changing sign, and so that ratio would change sign, and therefore the determinant would change sign. So that proves that this determinant function satisfies the second defining property of determinants. In the next video, we're going to continue this proof and show that this definition of the determinant satisfies the third defining property, which is linearity.